screen also.
Yeah.
Yes, fine.
We are live.
Okay. Okay. Good evening to you all. On behalf of Indian Physics Association, Roorkee Chapter, Physics and Astronomy Club, and Department of Physics, IIT Roorkee, I welcome you in this lecture series, Astro with ARIES. So this is the fourth talk in this lecture series and will be delivered by Dr. Manish Naja. I now request our Dean, Resources and Alumni Affairs, Professor Gurjar, to introduce the speaker.
Thank you, Professor Sumanta. And this is my pleasure to introduce my good friend, Dr. Manish Naja. We are sharing common interest in air pollution and climate change related activities. So, dear friends, Dr. Manish Naja is a senior scientist and chair of the Atmospheric Sciences Division at Aryabhatta Research Institute of Observational Sciences, that is ARIES, in Nainital. He has pursued doctoral research work at Physical Research Laboratory, Ahmedabad, and worked as a postdoctoral scientist at Japan Agency for Marine Earth Science and Technology, and also at National Institute for Environmental Studies in Tsukuba, Japan, before joining ARIES. He has been instrumental in setting up a high altitude atmospheric laboratory at ARIES and continuing high quality long term observations of trace gases like ozone, etc., and greenhouse gases and aerosols also using surface based, balloon borne, and ship borne instruments. He has been involved in different national and international projects and field campaigns. Presently, he is principal investigator of ISRO's atmospheric trace gases chemistry, transport, and modeling projects, and is leading a stratosphere troposphere radar facility at ARIES. So we welcome Manish, and I hand over this proceedings to Professor Sumanta or directly to Professor Manish Naja, please.
Yeah, thank you, Professor Gurjar. So over to you, Professor Dr. Manish Naja.
Okay, thank you very much. And it is nice to have more interactive session on this I believe. This is in the sequence of the series of lecture from ARIES, and today's lecture is slightly different, I will say. This is on the atmospheric science, focusing on the air pollution and climate study. So what I will do for the first half, or maybe around the 30% time, I would like to give this some introduction on this field. And then my major focus will be on the activity which we are pursuing in the ARIES. And maybe probably I am having some bandwidth issues, so I will switch off my video so that I think we have the smooth transition and the speaking, no lagging. Okay, so here you can see our institute is located at the mountain top and at the height of around 2000 meters. So this is the very ideal location. Now to go in the basically on the next step, why we are interested in this aerosol and the trace gases study over the Himalayan region. Whether you can hear me properly?
Yeah, we can hear you properly.
Okay. Not changing here.
Manish, you have to click on that slide and then move probably.
Yeah, right. Yeah, now it is okay. So the here I am trying to show the basically what are the basically our focus area. So when we talk about these different species like in air pollution and the climate change, they are basically you can divide in the two groups. One is the pollutant, which is basically in this area in the lower part of the atmosphere we call the troposphere, and where the major focus comes from the ozone, carbon monoxide, hydrocarbon aerosol, wide range of aerosol. But when we talk about the climate change, then we focus basically oriented towards the greenhouse gases, or you can say directly the common term is the global warming. And their species are basically related with the long-lived species, unlike in the air pollution. And I hope you can see also mouse. So when you talk in this, the greenhouse gases, they are basically long-lived. Long-lived, when I say their lifetime is more than few months or goes to years. And here the major species comes the is, CO2, ozone, methane, nitrous oxides, SCFCs or CFCs, whatever it is, and water vapor. I'm speaking water vapor lately because it is very highly variable. So when we talk on these gases, they are basically topic related to the global warming, sea level rise, and abnormal weather. Now, when we come back on the air pollutants, they are basically having impact on the health issue or the reducing the vegetation growth. And if you see in process wise, they are on the oxidation. When you talk in air pollutant climate change species or issue, they basically you can say enter the chemical, physical, and dynamical process in the atmosphere. And here on the bottom side, you can see the process is so complex, like from the urban pollution to the regional level, and then it goes to the global level, like it can transport from the one region to another region. And for here again, to make the more extensive analysis, you have to study the process and which are coming from the different sources, and then meteorology and dynamics, and then microphysics. So both these, all these things combinedly one has to deal with. And here, when we talk and put this related to the aspect of the, apart from the modeling, the observation part. So observation one has to have the involvement of surface observation and shipboard observation, airborne observation also. So like to give an idea like this, of course, this is a very familiar figure, but I'm trying to show in reference of the study we are talking on the air pollution and climate change. So when we talk on the air pollution, you see, like the air pollution basically limited in the troposphere or the lower part of the stratosphere. And here when the like species again, like emissions from the industrial emission, from the biomass burning, or from the automobiles. Whereas when you take in climate change, here the species or the you can see the in terms of the atmosphere, it is governing from the surface level to almost top of the atmosphere around 80 kilometer or above in that range. And again, the species are different. So here basically you see in terms of the space and the temporal, the air pollution is basically related with the few years event, and in the less lower altitude region, wherein the climate change is in the when you talk in the few hundred years, and it is basically governed in the up to 80 to 100 kilometer height region. So these are the basically different aspect in the. So what we are interested again, like here and trying to show very popular diagram, or the basically you can see the table, and which is showing the about the impact of the different trace species, trace gases and aerosol on the global warming. And this is the basically outcome of the extensive analysis by the IPCC. And here it shows the, of course, we know the quantification is better in the global warming or radiative forcing, but still there is large uncertainty. And here on the focus on this like this carbon dioxide CO2, and this radiative forcing is around 1.7 watt per meter square. And here you can see our understanding on this side, our understanding of the CO2 is very good or very high. So you say the level of scientific understanding, it is high. Other greenhouse gases, when you talk like methane or CO2 or the N2 or halocarbons, here also our level of understanding is also very high. Now, after these two species, long-lived species, if you come down in terms of the troposphere, you talk like the ozone in the troposphere can act as global warming, but in stratosphere it becomes the global in the it acts as the cooling. And our understanding in this process is you can see the medium. And its radiative forcing is very significant. I will say it is around total radiative forcing is around 0.3 watt per meter square. And per again, importance of the ozone comes here. If you talk in terms of per molecule, this radiative forcing is much higher than the CO2. Now, other species like these, apart from the trace gases, we come down and see no aerosol. They are playing a very complex role. And here is the major research focus is on, like the understanding on the radiative forcing by aerosol is very, very low. Like here you can see, like for black carbon or the other, the elemental carbon, organic carbon, our understanding is very, very low. Like you see medium And the complex again comes like black carbon, depending on where it is deposited, like black carbon on snow can have the positive radiative forcing. Positive radiative forcing is, and whereas on that is on the type of the land use, the cooling effect, and also the the direct effect and the cloud albedo effect, they are also negative. So you can see the our uncertainty part is very high. And so some people are also argue in the sense like when you have the aerosol cooling, it can compensate of the warming. But you can see on the net result, you can see the total anthropogenic effect. You can see it is almost 5 on the bottom side, 1.5 watt per meter square. So that means the global the warming is real in this aspect. Now here basically I'm trying to show one very nice example. Of course, this is the data figure has to be updated, but on the effect of the global warming on the basically on the regional scale on Himalayan glacier. And now here you can see on right hand side, this is the basically actual side photo of Himalayan glacier in 1978, and then in 1989 and then 1996. On the bottom side, you can see physically the width of the glacier is reducing. And if you talk in terms of the number, like in the 1960s, the glacier area in the Himalayan region was around 2,000 square kilometer. And it is coming down to almost the 1,500 or 1,600 square kilometer. And this is further reducing. And same time, you can see the aerosol optical depth, it is significantly increasing. So there is basically, you can see the direct evidence that you can have the warming effect of the over this Himalayan region. When we talk in terms of the air pollutants, so here I'm listing down some of the basic air pollutants in the atmosphere which we are concerned, or you can see criterion pollutants like carbon monoxide, SO2, NO2, and ozone, particulate matter, and lead. Now here you can see in the central, this ozone is playing a central role in this entire thing, and the more important, ozone is not directly emitted. It is basically produced by some of the pollutants that I will maybe explain slightly later. And here the major important point, like for the major source for this is basically combustion. And combustion means when I say it is incomplete combustion in any process. It can be in automobile exhaust, or it can be industrial, or it can be in home cooking. So this can lead to the emission of this particularly carbon monoxide because incomplete combustion means like basically oxygen is not sufficiently available for the combustion process. And now what is the basically ultimate effect on this? Like you have the health issue, you have the eye irritation and respiratory disease and asthma, and then it reduce the vegetation growth that I will show you in the next slide. And it visibility reduction, and the atmospheric oxidation capacity also changes, and radiative balance. When I talk in the, I was mentioning in the ozone basically play a central role in the atmosphere. And now here, of course, when I talk in the ozone, there are two different kinds of ozone. One, you can see the ozone in the stratosphere, which is almost 80% or the 90% in the atmosphere, and which is also probably no ozone layer you can see. And the another ozone lies in the troposphere, and this ozone is almost 10 to 15%. So what important point is like this ozone in the high altitude or in the stratosphere is the good ozone, and this is decreasing because of the depletion by CFCs. And there is another category of ozone in troposphere. This is bad ozone, and this is increasing. Now, what is the difference? You can see in the process-wise, production-wise, like stratospheric ozone. For ozone production, one need to have the atomic oxygen and the oxygen molecule, and combined in the presence of third molecule, it makes the ozone. And from where this atomic oxygen comes, in the stratosphere, it comes from the photodissociation used by the ultraviolet sunlight. We are in the sphere, the process is different. The atomic oxygen comes basically comes from the photodissociation of NO2. And in the troposphere, this precursor, when I say precursor, means some of the pollutants like carbon monoxide or hydrocarbon, NOx, they combine, and in presence of visible sunlight, it can produce the ozone. But this amount is very less. So you can say here, this tropospheric ozone plays a central role in the lower part of the atmosphere chemistry, like it is basically as an indicator of the level of pollutant that I will show you slightly later. How by seeing the ozone level itself, one can identify whether this site is cleaner site or it is polluted site. And here is the actual field observation showing how the high level of ozone can impact on the vegetation. Now, this is the actual field site, and you are seeing, and you can see on the circle there are some poles are erected, and in this area we are pumping the high level of ozone. And when I say high level of ozone, that means like it is measured in ambient air, the ozone level is around 60 ppb, and here double amount of ozone, like around 120 ppb of ozone is injected in this area. So when you inject the high level of ozone, what happens to, you can see the environment, or you can see in the impact on vegetation, that you can see here. Like here you can see in this area, when you inject the high level of ozone of double amount, the temperature increases in this area. Temperature increase means, like in the sense, like background temperature is around 30 degree, and in this area you can see temperature goes to around 33 to 34 degrees centigrade. Now, this is nothing but, of course, one should not confuse with the global warming. This is not the global warming. It is basically effect on the vegetation, because the high level of ozone reduce the transpiration in the vegetation. And when reduction in the transpiration, rise the vegetation temperature. Now, so because increase in temperature, the vegetation growth reduces. And here we can see the actual plot. This is based on the theoretical model. And you can see the response on the different vegetation. On the right hand side, you can see here, like you can see when the ozone level in the atmosphere is around, you can say the 40 ppb, the almost yield is 1. 1 means like the 100% production of the vegetation is happening. Now, when you make the ozone, and you can see in terms of the cotton or soybean or peanut, the productivity almost reduced by 50%. You can see this 0.6 or 0.4. So you can see the significant reduction in this. Of course, it depends on the other types of the vegetations, or you can see the effect on the sorghum or the wheat corn if is slightly lesser, but you can see it is very significant on the other species. So this is the very actual field observation, and we're showing how the high level of ozone can reduce the impact growth of the vegetation. So apart from the health impact, we have the direct impact on the vegetation, and such experiment has been done in the different groups in India. Now, so here I'm coming back, like why we are interested in this the air pollution, particularly like our interest is on the northern Indian region. So here I'm trying to show, this is the on satellite picture showing the basically smoke on the northern part of India. You can see very well. Now, similar thing, you can see this is another theoretical estimate of carbon monoxide. You can see the very high level of carbon monoxide in the northern part of India. And this is also popularly called the Indo-Gangetic Plain, which is highly populated in the industrial region. On the, you can see the on left hand side and bottom, I'm showing the population density here, and this population density is very high. Now, one important indicator again related with the ozone, like here you can see the Indo-Gangetic Plain northern part, you can see high population density going to almost more than 1000% per square kilometer. And similarly, you can see in China and this part the high population density. Now, these are the basically directly related with the high level of tropospheric ozone. Now, this is the basically first estimate made by the Fishman to drive the tropospheric ozone. Here, I would like to point it, like the tropospheric ozone retrieval is very difficult from the satellite. Presently, there is no satellite giving the direct observation of the tropospheric ozone. Now, this is basically methodology developed by making the total ozone and then subtracting the stratospheric ozone. So basically, then you get the information of the tropospheric ozone. So here you can see directly in northern part of India, here, this is correlating with the high population density. And this is basically, so again confirming, like whether it is carbon monoxide or aerosol or other species, they are very high in northern part of India. And this black dot is showing the basically our location. So here I'm just again trying to point out, like our location is very ideal to have this such kind of study. Now here I'm trying to list down some of the factors which are affecting the this region, or you can say over the Himalayan region or northern part of India, like we are having the regional emissions, we are having biomass burning and forest fire in this region. Of course, I will be covering this each aspect one by one. Then we have the effect of the long range transport dynamics and the background level. Like this is very important, like how much the contribution of the background level. On the bottom side, here I am trying to show the influence of the air mass from different region, and this we call the back air trajectory calculated from the for the Nainital. That means the theoretically we make the basically estimate to assess the how the air is coming from the last of 7 to 10 days. And this is the basically indication like how one region can affect from different region. So here you can see, if you see one by one in the month of January or in the winter season, the air mass from the Europe or Africa can reach to this region over the Himalayan region. So here you have the effect of this the pollutants coming from Africa and Europe. And whereas in the you can say systematically in the springtime, the air mass is very slowly moving, and you can see it is we have the local effect from the basically the subcontinent region itself. Where in the monsoon time, you can see the air mass coming from the marine region of Indian Ocean, Arabian Sea in the month of June, this yellow color. And then in again September, it is coming situation is something like as in springtime. So you can see notably here the springtime or autumn time, we have the very slow moving of the air. So you have the very dominating effect of the local emission. Now similar thing you can try to see how is the basically okay. Now here I'm trying to show on this green color the effect of the long range transport, and here I try to see in the percentage in terms of percentage over this Nainital, or you can say representing as the Himalayan region, including the you can say the Henle, how much percentage of time in different year or in different months you can have the contribution of the pollutants coming from Europe. And here you can see I'm pointing out in the winter or springtime, early springtime, almost 40 to 50% time you can see the air mass coming from the Europe. So you have the basically effect of the pollutants from the different region also, apart from the local effect. Now here another, like whatever I said, you can understand here in the very simple term. Like here, this is the land mass, you can say the India, and this is the Bengal, and this is the Indian Ocean. And we are located in the Himalayan region. So whatever the pollutants emitted from this region, they are basically getting trapped, and we are also reaching to the Himalayan region. So this is a very nice example of showing that we are located or in this region is very ideal natural laboratory, where one side you have the mountain kind of thing, and another side you have the source emission sources coming, and they are mixing. So clean air and the polluted air mixing on different time of the year. So depending on, and here they again similar thing I'm trying to show in the pictorial bay. Like you can see, this is the basically Delhi and Nainital. We are located mountainside, and in the winter time we have the basically the pollutants coming and from Indo-Gangetic plain and going to marine region. And you can see the effect from IGP region can also have significant contribution of Bay of Bengal. But in the monsoon time, this clean air is from marine region is going over the landmass. So here you can see the location by this is very well suited location where you can have the effect of the long range transport and how much contribution going to clean region. So that is kind of assessment one can make over the observation. So I am coming to the basically the observation location here, and so basically we have the 4 locations or 4 observation sites, and depending on our interest on camping mode, we make observation. So the ARIES is located here, and you can see the mountain series is around 2000 meter, and if you go slightly above, like 100 kilometer above, the mountain series of around 4000 meter you can see. And we are also having the another the site Devasthal, where also you might have heard, like in the previous lecture, we are having the very large telescope of 3.6 meter optical telescope, and so we have also have campaign vision, and now we are also trying to set up a full-fledged the laboratory at Devasthal site. We have another observation and then collaboration mode in the Pantnagar and Dehradun. So these Pantnagar and Dehradun are they are basically treating as a basically site representing for the source region. So we try to see how much is the basically the level of at the source region and how much is reaching to the mountain side. So this kind of combination we are trying to do and then understand the process. So here, like you can see the study at the ARIES, you can basically divide in the basically 4 component on the trace gases and aerosol and the meteorology and the dynamics. And to historically, like of course, the ARIES was set up in 2004. Of course, it was this old observatory and the astronomical observations were being made, but the atmospheric science activity started when the formation of the ARIES was done. So the aerosol studies of aerosol optical depth and the black carbon were started in 2004, and then systematically trace gases observation also started in 2006. And apart from the surface observation, we also do the balloon-borne observation and the lidar-based observation, and systematically these are being added up. And apart from the direct observation, we are also involved in the modeling and the satellite data analysis. And considering this location, I would like to point out here, we have also the 3 big international field campaigns were also conducted at this site. It's like one is the GBES, Ganga Valley Aerosol Experiment, and the SISQUAT. It was basically combination of the different the country, and this Statoclim. This is basically European funded project. So several international projects you can see, these are the international project, and some national the campaign are also carried out, and we have also participated in those campaigns. So here I'm trying to show the list of the instruments which are basically we are heavily having here, and that you can see we are focusing on the surface and the balloon vane and the lidar based observation. So we have the, you can again divide in the 4 component on the trace gases and aerosol and the meteorology and dynamics. So on the trace gases, we have the ozone and supported the precursor gases on online instruments. And some of the observation we are also doing offline. Offline means like we are collecting the air sample from different places and then bringing back at laboratory, like particularly we have set up the gas chromatograph for observation of hydrocarbon. So that we are doing the offline analysis. And apart from the surface, we are also having the balloon-borne observation of ozone and meteorological parameter. And then we are also having the greenhouse gases in collaboration with the NIS Japan, and also we have the online instrument, CRDS. This is very new technology with cavity ring down spectroscopy. And this is very highly precise, and we can have the observation in the basically less than a second's time interval. So this are, we are having the greenhouse gas observations, so offline and online. And then we are also having the MaxDOS. This is also in collaboration with the Japan Chiba University. And this is one new technology instrument, MaxDOS, which is basically we are also some of the instruments are also put on the satellite. So this instrument is very ideal for the satellite validation. We are having the meteorological tower here, and this is, you can see here this photograph here. And for having the boundary layer study, and we have the observation at the 3 to 4 level, and extensive observations are being made with this meteorological tower. On aerosol, we have in the Himalayan region, we are having oldest observations of aerosol optical depth and the black carbon, and we have also added the observations instrument for the organic carbon and elemental carbon. And we are also having the aerosol number concentration in the different size range, and nephalometer and aerosol and the aerodynamic particle sizer. So we also have the sampler to make the chemical analysis. We are collecting the sample and then doing the chemical analysis. So for the aerosol, we have the optical, physical, and chemical property study. And of course, we are having the one lidar which is operational recently for the observation of the aerosol. And of course, this has been operational in the 2010, and then again now reactivated. So we are trying to cover the different part of the atmosphere. Now, one major facility which is recently activated, and that is the ARIES ST radar. So this is the very, I will be covering this more detail at during the result part. And here, this is the basically capable of measuring the winds in the atmosphere up to 20 kilometers. So basically, we are crossing the tropopass, and so doing the study over the upper troposphere and the lower troposphere. And more detail I will be covering slightly later. And here you can just, I would like to show the on the top, you can see the antenna array. This is the 588 antenna array on the mountain top. And this is the basically the technology was very challenging, like to have this kind of the big array on the building top. And also you can see this TR module, transmitting and receiving module, those are hanging from the rooftop. So I will be going in more detail on the later part. So this is the, again, you can see it, a nice view with the mountain and the cloud, the antenna array on this region. So now this, as I was mentioning, like considering the importance of this region, the ISRO has the major interest, and they have funded a different experiment. And here I'm trying to show this ARIES Nainital is one of the main observatory under the ISRO project, covering the three high altitude mountain. Like this is Nainital in the northern part of India, and then in west there is Mount Abu, and the south is Ooty. So we are a part of the, we can say, the main campaign for the setting up of the laboratory. And under this program, we are having the observation of the trace gases and aerosol and the boundary layer meteorology. So here to give an idea like importance of this site, like I'm trying to show a figure showing the ozone variation at the 4 observation sites. As I was mentioning, we are having observation at the Devasthal, black line you can see, and this is the diurnal pattern from 0 to 24 hours in average picture. And the green color is showing the Nainital, and the red color is showing Pantnagar, and the blue color is showing Dehradun. Now, if you remember, I was mentioning the ozone is produced by photochemistry involving the pollutants. So here you can see this Pantnagar and Dehradun, these are the low altitude side, and you can see the diurnal pattern ozone. In daytime, ozone levels are higher. That is basically indicator that the site is polluted. So that means because of the pollution, you have the solar radiation and it is leading to buildup. Whereas Nainital or the Devasthal, they are the mountain side and rather cleaner, so level of the pollutants are lower. So you see almost flat kind of thing. And that means, or indirectly, you can also see you don't see the daytime buildup. Of course, you can see slightly dip. That is the very much totally different. That I will come. This is the basically role of the dynamics. So that is the different aspect. So we should not, I think, go in this mode like it is not flat. So you can consider this a flat kind of thing. Main aspect is the daytime photochemical buildup is missing at the Nainital or Devasthal. So confirming that these are the clean sites. So again, this is shows that ozone can also play or can also be a very good indicator. In the bottom side, I am trying to show the comparison between the Nainital and the Pantnagar, and you can see the role of the dynamics very well. In daytime, when the pollutants are lifted up, you can see very nice the positive correlation. But the night time, they are basically pollutants and down, so you can see this and the pollutants levels are much lower. Again, you can see the very contrasting result, like again importance of the boundary layer and how the low altitude site or the high altitude sites can behave differently in terms of the pollutants. Now here I am trying to show the Pantnagar and the correlation between the boundary layer and the black carbon or carbon monoxide. And here you can see in the winter time, the basically very low level of the black carbon or the organic or the carbon monoxide when the boundary layer height is very high. Or in contrast, you can see here on the bottom side on the Nainital, the organic carbon. Organic carbon also you can see indicator of the aerosol or the carbon monoxide, and they are showing very positive correlation. So that means this the in the daytime when the pollutants lifted up from the surface side that goes to the mountain side, and they try to behave differently. So here you can see the contrasting effect on this side. I'm trying to just give you a feeling how the other pollutants level at the mountain side. And the first one is basically you can see is the basically on the ozone, and then this is the carbon monoxide and NOx. And here you can see the levels of the carbon monoxide or NOx, they are very low, like in the range of PPT, like 1 or 2 ppb, or you can say 1000 ppt. So this is some kind of confirmation this Nainital side is rather clean, but it is not always true. That you try to show in the second panel, where the level or variability is much larger. So this is, I will be just trying to show why springtime this behavior is happening. And again, you try to show in terms of this green panel, the ozone, where you can see the Darwin variability is slightly different. And here you can see the some role of the photochemistry, when you can see some tendency of ozone buildup. So this I will try to focus on the more on spring, when you have the more the other species like carbon monoxide. We have the setup. We have set up with gas chromatograph. That is a very nice facility, and we do the analysis of the hydrocarbon from different region. And here I try to show the one difference when you can try to compare with other IGP site. Like you can see short-lived species, they are much higher in the other side, but in Nainital or the Pantnagar, even the plain side, the levels are much lower. And again, this observation, some of the hydrocarbon, you could try to see a correlation study, and then you try to identify sources. Like here, this one, the high correlation in butane or propane, or you can see butane and ibutane and n-butane. They are trying to confirm that these are the coming from some LP. Or when you try to make the correlation between short-lived or long-lived, then correlation is not good. So that means they are on this period of time, they are not coming from the common sources. So this is the another the methodology we have tried to identify how the different sources or the emissions from different sources are impacting this Himalayan region. The other aspect we are also covering on the effect of the biomass burning. Like why we are interested in biomass burning? Biomass burning because they are having the emissions of the different trace species, particularly carbon, black carbon, carbon monoxide, or NOx or aerosol. So we are interested in that. And here this we try to make the analysis of the modest fire count data. And and also here you can see the trend study. Now I would like to draw your attention here. This one, this is the basically the modest satellite figure, and showing the how the global on the global scale the biomass burning is basically changing in different season. And we can see on the globe, and the season wise it's changing, like in April, May, June, July, August, September. And you try to see here the in globally the Africa or the South America, they are the region when throughout the year burning. But if you focus on this the blue circle, the Indian region. So Indian region, you can see the major biomass burning comes in the month of spring. Like here, this is spring, like April, May, like here. So, okay. So on the springtime, you have the major biomass burning, and after that you have the reduction. So then we try to assess how on the southeastern region and northern India this is changing. So we try to make the analysis of this fire count over the northern India region, and the top panel you can see in the modest, like in the again you can see peak in the month of April and May. And so this is the basically period when you have the more biomass burning. So our interest is basically on see how the biomass burning emission species like the black carbon or NOx, they are impacting our atmosphere. And our interest is also trying to see the radiative forcing. Like when you have the biomass burning, how much change in radiative forcing is made. And we have estimated like when the biomass burning is dominating, like in this black line here, and then biomass burning is not or very less, and you can see the very significant warming in the atmosphere. And that's because we are considering the contribution of the black carbon. So that is the basically our again the analysis, like how you can see the impact on this Himalayan region. And not only surface, now we have the balloon facility, so we try to see make assessment of the impact on the ozone. And apart from the surface ozone, here you can try to see on this figure in different year the enhancement in ozone in the altitude of around 6 kilometers. Like this red line is showing the ozone changes in the when you have the high fire activity, and the green line is showing when you have low fire activity. And you can see almost 20 ppb of ozone enhanced in the altitude region of the 4 to 5 kilometer region. So this is also another important aspect one has to see, like impact of this biomass burning not only in surface but at the high altitude side. Now we also try to make assessment whether this impact is consistent in different part of India. And so we have made a comparison over the three regions like this red dot is showing the our location Nainital, and then green is the basically in the central part of India, and the blue color is showing the western part of India. And here on this side, you can see this the level of ozone throughout the atmosphere, like in the up to you can see the middle or the lower troposphere, the levels of ozone are much higher. Now, this level, if you try to compare with western part of India, here you can see the springtime. Now, the levels are very significantly high, and again in the lower part of the atmosphere, like in 2 to 3 kilometer up to 4 kilometer. So that is again confirming the dominance of the biomass burning could be much larger in this in the northern part of India, or you can Himalaya. Now coming to the another aspect, we are also on the aerosol study of the result I have shown. Like here, some of the unique result I am trying to show here in terms of the aerosol. Now this is the basically our first observation made over the central Himalayan region, and you can try to see the aerosol optical depth level is very low in this part of Himalaya. So, like optical depth is almost the less than 0.2. And if you try to see in terms of the radiative forcing and try to compare with the other urban sites, the radiative forcing is much lower over this part of India. Like here, you can see the atmospheric, the warming at in this in the over the Nainital is a 4.9 watt per meter square, whereas in Kanpur or Bangalore it is 71 and 28 watt per meter square. So this is again confirming that this approach the on the in comparison this the site is clean, but when you have the some events, you have the transport of the pollutants, and then you try to make assessment. And here again you can see the impact of the long range transport of the pollutants, and here the assessment made over the when you episode on the when the aerosol particle is coming from the Thar desert, and you can see back a trajectory. They are the transporting the pollutants or the dust over the Nainital. So this you can see the pollutants or the dust can also reach over this Himalayan region. Now here you can see the aspect, like we also try to do the modeling and try to understand how much the you can see different component of the aerosol in over this region, and we try to segregate. Like here, the comparison of observation and model is pretty well, I will say, considering the difficulty, and we try to segregate the effect. And using this geoscom model, we have shown that inorganic aerosol is contributing almost 42% over this part of the Indian region. Of course, it has this seasonal variability, and which is we can say the more contribution it is say in the June, July, August. Whereas you can say the role of the dust is also significant in the month of the March, April, May in the springtime. Here almost you can see making this aerosol optical depth almost 0.35. So that is the basically the understanding we are trying to make on the how much contribution of different sources of aerosol are having in this part of. As I was mentioning, we are also having the one very nice meteorological tower, have the extensive observations of the boundary layer study, our major focus on that, because the boundary layer play a very important role. And here you can see the example of the Darwin pattern, and here on the bottom side on the different season. So you can see there's the boundary layer can reach as high as almost the 1500 meter over in the daytime. But interestingly, you can see, of course, we were not expecting, but in the month of the spring, or you can in the March, even up to the late hours, you can see boundary layer of slightly high. But again, you can try to see how it is having the impact on the different season, like in this year in the month of December and in the March. Again, you can see in the month of the December in winter time, the boundary layer is much lower, almost the 0.5, or you can see 500 meter. Where in the springtime, it can goes up to, you can say, the 1500 meter to 2000 meter. So that is the basically you can see again the making the direct assessment of observation of boundary layer height, and then how it is impacting on the trace gases and aerosol. Now here I am coming to the basically the last leg of my the topic and slightly more detail on the ST radar. So as I was mentioning, like we have this facility set up with the funding from the DST, and this is the, I will say, unique facility in the northern part of India or in the Himalayan region. Now, this is the radar having the element array of 588 element, and these are the Yagu, the antenna set up in the circular the pattern, and each of the TR, this is the basically you can see the active phase, the radar. So each of this the antenna is connected with the transmitting and receiver module. Like here that you can see below this the rooftop, so are hanging from the ceiling. So these are again the TR module 588. Now here you can see bottom side, this is the basically you can see pattern of the our array. Like this is circular aperture and the hexagon, each of the like 588 antenna, we are again divided in the 12 cluster, and 12 cluster, each 12 cluster is having the group of the 7 hexagon. So they are basically you can say the making the entire cluster very strong. Now here is the basically again you can see this antenna on the rooftop, and this is the basically data acquisition room or the you can see radar controller room, which are having the basically you can see the supply unit, or you can say the DSP digital signal processing unit, and you can see the RF front end receiver here mounted here. So this is the basically lying at the bottom of the on this TR module floor. Here again I'm trying to show here this one. We try to make this observation, and again to over the radar observation, we try to again make the comparison with the balloon wind speed or wind direction, or the meridional wind and zonal wind both. So we have made extensive observation, and here I'm trying to show just one example, like the observations using the radar at the balloon. They are almost showing the very result. Of course, one should not expect one-to-one the one-to-one correlation in this, because the radar is basically more making observation in the point observation and vertically in the zenith direction, whereas the balloon goes drifted in the because three different balloon, so it can it goes up to 50 kilometer or the 100-kilometer region. But considering that aspect, you can see this comparison is very good, very good. And you can see the wind direction is basically in this period, like this is the April, and so this is the mostly westerly to the westerly to northwesterly. And here you can see this very high wind speed of around the 30 meter per second, and that is basically confirming the existing of the westerly jet in this part. So this is the one typical example of this. And then we also try to understand the turbulence parameter, and like because this is the first radar of the northern India, so the turbulence parameter we were just making the assessment. So basically, okay, that I will this one, and here you can see this is the basically first estimate of the turbulence parameter over the northern India. And here we are also surprised, like this value are much larger or order of difference than the southern part of the India. So this is basically again showing the how importance of this the region. Very interesting result. Like we have the events of the very heavy rain or hailstorm, and that is you can see very well detected by the different beam of the radar. You can see the power spectra, and that is showing the almost up to, you can see the precipitation echo up to 10 kilometer, you can see very nicely. So this is the another capability of this radar. Apart from the wind, you can also make the precipitation study, but of course one has to make more the analysis on this part. Here, so I was mentioning this GBEX campaign. So extensive observations were made in collaboration with this US Department of Energy and ISRO and ISC Bangalore. And so of the result part, I am not discussing. Some of the result already has been discussed. So here I am trying to campaign are conducted. Now, apart from this campaign, like the one European funded project, one Statoclaim, They also have made the extensive observations of the balloon wall, ozone, and the aerosol and water vapor observation over this our region. Now here another I'm trying to show this campaign, like considering this importance of this region, the extensive observation were made over the Himalayan region and the Kathmandu Valley. Like we also participated in this experiment, and a major the interest was basically on to see how much impact of this pollution from IGP or the biomass impact is having over the Kathmandu Valley, and also the how local sources or local the basically the burning from the Kathmandu Valley is transporting toward the Indian region. So that kind of the assessment is made in this campaign. Of course, the many paper has come and there has been a special issue on the for this also. And we also have, of course, a lot of the meeting and science workshop and training course to basically give training for the student. And like the last year, we conducted one international science workshop at in Nainital, and in that basically you can see the 33 scientists and students participated from 7 countries. So we are also having this kind of activity for training for different people. So basically, the involvement of the students and the young scientists can also be made in this part. Now, at the end, I would like to say there is a lot of scope for collaboration and involvement. Apart from the science theme, of course, this consider the importance of this in the region. There are a lot of science theme where the scientists can involve. But I'm trying to just point here only a few things where the student which are from the basically on the undergraduate or the PG level, they can involve directly. And like for example in instrumentation part, like development of this we are trying to make the development of the transmitter and receiver module for the ST radar, because yeah, one point I would like to mention here, like there are basically network of radar in India. Like right now the 3 radars are active right now, and the government is planning to set up more radar. So there is a lot of scope on this part. So this right now the transmitting receiver module, they are basically heart of the system. So there is a lot of scope of involvement of the student from the electronics department or the other division in this part. And the software development for this ST radar, that is also having the lot of scope for the graduate and undergraduate student to involve and to have this development. And the major thing where the ISRO is also very much interested, and we have done some analysis using the inset data, and we try to make this the availability of the satellite retrieval. And here I'm trying to say the involvement of the student; those are very keen on artificial intelligence and machine learning and the utilization. Here, this is the one aspect where I can see the different student from the other, not only physics department, but the electronics or the other group can also involve. And again, I would like to mention, like I missed one point, like we are also having the one the work model where we try to see the effect of the pollutants, and here the hydrological department can also have involvement. How there are different component of this on the WARF camp, where this impact of the meteorology dynamics and on the water cycle can also be assessed. So with this, I would like to say thank you very much for your kind attention and time for this. Thank you.
Okay, thank you very much, Dr. Naja. So we have few questions now.
Yeah, I will just
first. Yeah. Okay, the first question is how the recent pandemic affected overall climate of India.
Yeah, right. And because of shortage of time, I could not involve some of the things. But I think say it is basically two-way impact of this. Like you can see at the surface level, like we have also seen there is reduction in the level of some of the pollutants. When I say some of the pollutants, there are some pollutants like particularly ozone has shown different behavior, as everyone is expecting, because during the pandemic time the industries are shut down, so you have the reduction of the pollutant. So, but it is not consistent. It is basically shown the mixed effect, like reduction only in some part of the India, but not entire Indian region. And particularly we have seen like increase of some of the pollutants, particularly ozone, even CO over the northern part of India. So it is basically, I will say, the mixed kind of thing. But on general metro city, it has shown significant reduction of some pollutants.
Okay, the next question is there any practical and affordable technique to capture the atmospheric carbon dioxide and thus reduce its level?
Yeah, right. I think that also very good question. This is, of course, I will say technology is being developed. It is, but affordable is a issue here. It is very, very costly. So now maybe there are the process to reduce the cost, but the technology is still in development phase and it is being used in different places also. I will say very good research, the theme for the future research.
Okay, the next is with the current facilities at ARIES, can we observe the spectral line observations of various radicals and molecules in the atmosphere?
Sorry, can you repeat spectral line?
Yeah. So with this current facilities at ARIES,
Yeah.
can
Right
we
now,
observe?
Yeah. Right now, we are not having those instruments at ARIES.
Okay. So next is why the weather prediction works only for around a week durations. What are the computing challenges and how the scientists at ARIES can deal with those computation challenges, complexities of challenges?
Yeah, right. I think now the need of the nation, I will say, like, and also when we say prediction, like here there are two components. One is the meteorological prediction, another is the chemical prediction. That is the chemical weather. So I will say right now the challenge are not very much or not very tough for the like 3 to 4 days forecast. Now major problem or major challenge comes when make the forecast for like from 5 day or 6 day to 10 days or 15 days. So that is the basically very much challenging period for meteorology and for chemical. Like now, and we are doing, of course, we are not doing the officially forecast, but we are using the work model. We are having the meteorological capability for making the basically you can see simulation, meteorological estimate. Dr. Naren Singh is involved in that, and we are doing the simulation for the chemistry part, and we have the capability and we are doing it. But again repeat that more challenging is basically prediction for you can say 7 days to 15 days or 20 days forecast for both meteorology and chemistry.
Okay, I think there is no other questions. Okay, so if you have any other questions, you can type in the chat box. Yeah, so one question from my side, like you know that ozone is like in troposphere, it is very like it is not good for human health, and in the stratosphere, if the ozone goes, the ozone density increases, it is good for us. So some of the pollutants do the reverse, right? To increase the ozone in the troposphere and decrease the ozone in the stratosphere. So what are the pollutants actually, or what are the greenhouse gases that do it?
Yeah, if I understand your question properly, like the pollutants are totally different, which are affecting the ozone in the troposphere and stratosphere. Like in the troposphere, they are basically short-lived species. Like for example, critical role comes from the NOx. And when I say NOx, means NO and NO2, and then carbon monoxide and hydrocarbon. They are basically leading to ozone production in the troposphere. Now, their amount is not very much in the stratosphere. They are less than 1 pppt. So they are not doing any role in the stratosphere. They are basically, and in case of stratosphere, basically CFCs, or you can see the HOX or they are playing a role for the ozone destruction. In stratosphere, the ozone formation is natural by the oxygen oxygen molecule. So basically, in the stratosphere, ozone is perturbed by the destruction process, whereas in the troposphere, ozone is perturbed by the production process. If I
Okay,
whether I need
okay.
to
Yeah, okay. All right, I hope there is no other questions. So on behalf of organizing team, I take the opportunity to put forward the vote of thanks and acknowledging the support of all the team members in organizing this lecture series. I thank Dr. Manish Naja for delivering such a wonderful lecture today. I thank Physics and Astronomy Club team members, which comes under Student Technical Council, IIT Roorkee, for their support in organizing this lecture series. I thank Professor G.D. Burma, our head of the department, Physics Department, and President of Indian Physics Association, Roorkee chapter, and the team members for organizing this lecture series. And special thanks to Professor Gaurav Shetty for being instrumental in this lecture series and to help us in organize this lecture series. And at the last, I thank all the audience for attending this lecture. And thank you very much to all, and good night and stay safe.